Hello and welcome back. In the previous few lectures, we looked at hypothesis testing when we are comparing the means of two populations. And in this lecture, we are now going to look at the situation when we want to compare the proportions for two populations. Okay, so again, we have this table with the test statistic, and we can see that the test statistic follows the normal distribution, and that is when we are working with independent samples and large samples. So again, let's have a look at an example. A manufacturer of microprocessors buys its processors from two suppliers. A random sample of 300 chips from supplier X resulted in 50 defective chips, whereas a sample of 400 chips from supplier Z resulted in 70 defective chips. Test at a 1% level of significance whether the proportion of chips that was defective from supplier Z is more than that from supplier X. Okay, by now you should be very familiar with the steps in hypothesis testing. So the first step would be to set up our null and alternative hypothesis. Okay, so remember that now we are working with proportions and no longer with population means. So we have the proportion defectives for supplier Z equal to the proportion defectives for supplier X, versus the alternative that there are a larger proportion defective chips for supplier Z than for supplier X. So that is a one-sided alternative. It's one-sided to the right. And we are working with a level of significance of 1%. Remember, just a little bit of revision. The alpha, our level of significance, is the probability of a type 1 error. A type 1 error is when we reject the null hypothesis when in fact the null hypothesis is true. Okay, and then we substitute our sample information into our formula, into our test statistic formula. So if we go back to our summary of this hypothesis, we have our test statistic that follows the Z distribution or the normal distribution. And for that formula, we also need the pooled proportion. The pooled proportion, which is indicated with P star, is given over here. Okay, so let's do the substitution. So first of all, we calculate the P star or the pooled proportion. That's the number of defectives in Z, that is what my XZ stands for, plus the number of defectives from supplier X. So that is 70 plus 50. And then we divide it by the number of items from supplier Z, that was 400, and the sample size from supplier X, which was 300, and then we get a pooled proportion of 0.1714. And that is what we will substitute into this test statistic formula here. Okay, then we also need the sample proportion for supplier Z. So that would be the number of defectives from the supplier, which was 70, over the total number, which was 400. And that will give us 0.175. And then the sample proportion for supplier X would be the number of defectives, 50, over the sample size of 300, to give us a sample proportion of 0.167. Okay, and now we have everything we need, and we can proceed and substitute it into the test statistic formula. So P hat Z is 0.175, P hat X is 0.167, and then below the line we have, in the square root, we have P star, which we've calculated previously, times 1 minus P star times 1 over sample size for supplier Z, so that's 1 over 400, plus 1 over sample size for supplier X, that was 300, And if you calculate that, you get an observed test statistic of 0.28. So now in step 4, we will find the rejection region. Okay, so because our test statistic follows the normal distribution, we will find our critical value from the Z distribution, and we are testing a right-sided alternative. So our critical value and our rejection region will lie towards the right tail of the normal distribution. Okay, and if this is my normal distribution, then my critical value will lie towards the right, so that the area to the right of my critical value is 0.01, and that's because my alpha is 0.01 or 1%. So the area to the left will be 0.99, and then you can find Z 0.99. You can find that from your Z tables, or you can use statistical software, and that is equal to 2.326. Okay, and sometimes we also refer to this. It just depends on the tables that you are using or the textbook that you are using. Sometimes the Z is also referred to as Z 0.01. Okay, so my rejection region is this red area, and my observed test statistic was 0.28. So this is 0, and 0.28 will lie somewhere around there. So clearly my observed test statistic falls in the acceptance region, and therefore we will conclude that we do not reject the null hypothesis. Okay, so here we have that our observed test statistic, which was 0.28, is less than my critical value. It does not lie in the rejection region, and we do not reject the null hypothesis. We can also make use of the p-value method. So the p-value method is, if this is my normal distribution, this is 0, my observed test statistic value was 0.28. Because I'm testing a right-sided alternative, my p-value will be the area to the right of my observed test statistic. So my p-value will be that red area. And again, you can find this p-value by making use of the standard normal tables, or you can use statistical software like Excel to find that probability. So you will see here that the probability of the red area, the area to the right of 0.28, is just 1 minus the area to the left of 0.28, and that is 1 minus 0.6103 to give me a p-value of 0.3897. Finding the p-value is really just revision from work that we've done when we did the normal distribution, and we've calculated p-values multiple times in previous examples. Okay, and now my p-value of 0.3897 is more than my level of significance, which was 0.01, and therefore we do not reject the null hypothesis. So we get exactly the same conclusion whether we make use of the rejection region method or the p-value method. And then our final conclusion, we say that there is not enough evidence at the 1% level of significance to conclude that a proportion of chips that was defective from supplier Z is more than that from supplier X. We can quickly also find the critical value and the p-value in Excel. We have done this many times before, so if you are comfortable with that, you can skip this part of the video. And we want to find your critical value function. We make the area to the right of norm dot observed test statistic value. Inverse function. Remember,
find the
the S
area
stands for the
to the
standard
right.
normal distribution.
My critical
And the probability that we
Uta,
type
bly
in
bietjie
here
stil.
is the area to the left of my critical value. Because we are testing right-sided, the area to the right of my critical value is alpha, 0.01 in this case. And therefore, the area to its left will be 1 minus alpha, 1 minus 0.01, which is 0.99. And there you get your critical value. And then for the p-value, we make use of the norm dot s dot distribution function. My observed test statistic value was 0.28, and we are working with the cumulative distribution function, not the probability density function, so you can put in a true or a 1. So this is the area to the left of my observed test statistic value. So to get the area to the right of my observed test statistic value, I will subtract this probability from 1, and that is my p-value 0.3897. And you can compare that with what we have on this slide.